Okay, thank you for joining today's webinar. My name is Greg Watts and I'm the Marketing Director here at Terabee. I'm joined today by Dr. Jan Koverman, our Chief Technology Officer. Jan's going to give the bulk of today's presentation, and we'll get into that in just a couple of minutes' time. Jan, if you can just flick the next slide on, please.
Of course I can. Good afternoon, everybody.
So before we get started, just a couple of words about Terabee. So we were founded in 2012. We're a very international team, 18 nationalities at the last count. We're multiple award winners. I've been recognised by a number of organisations as being a very innovative company to watch. We've released 20 plus hardware and software products to market and sold tens of thousands of products. We're very proud to be a CERN technology partner. We have 45 plus months of joint projects with them. They literally are almost right next door to us. We're nestled on the French side of the Swiss border, just 5 kilometers from Geneva. And we're very proud to work with CERN. We get access to their facilities from anything from the tunnel of the Large Hadron Collider to their offices and conference center and so on. Next slide. So Terabee is a sensor and sensing solutions company. Our core expertise is in optical time of flight, and that's of course the subject of today's webinar. That lends itself to LED rangefinders and distance sensors, 3D time of flight cameras, but we also have expertise in thermal cameras and radio frequency technology. And all of this is underpinned by appropriate algorithms, in some cases control systems, and in some cases software as a service. Next slide. So as you'll see on the left-hand side here, we produce a wide range of sensor modules. This is by no means exhaustive. But we have time of flight distance sensors and rangefinders at different price points and different performance. Generally, for any given price point, we tend to have the highest performance, whether that be in terms of range, update rate, or perhaps the size and weight of the module. We also have a unique way for people to build custom sensor arrays, almost a plug and play approach. I think we're the only company to do that. And as I mentioned previously, we produce 3D time of flight cameras. Watch this space because we have some more news coming here soon. And we also have this expertise with thermal imaging, and we have a range of infrared thermal cameras as well. So we take that foundation technology, all of which I should say is available for sale on our website. You can find the full range on terabee.com. Our sensor modules are also available from a range of distributors, including Mouser and DigiKey, and some more regional ones as well. Again, if you go to our website, you'll find those resellers. So we take that technology and we also build what we call application products. So our time of flight distance sensing goes into solutions for stock level monitoring. That serves, for example, the agriculture market for grain silos or animal feed silos, water treatment plants, manufacturing as well. And we also have harnessed our 3D time of flight cameras to build solutions for smart buildings, notably people counting. And these solutions are great for systems integrators or end users that need a complete solution rather than building their own. When it comes to Industry 4.0, we take our foundation technology and we package it up in an appropriate way for that market. So that means industrial communication protocols, more robust enclosures, IP ratings, and we also add intelligence on board. So you can set the sensors up to set certain thresholds and trigger alarms should those thresholds be breached without needing to do a lot of complex programming. We have a long history with mobile robotics. We've got a lot of customers in both the drone and the ground robot market that have used our time of flight distance sensors for collision avoidance and navigation. But we've gone a bit further as well. We've used our radio frequency technology to create kind of indoor GPS for GPS denied environments, high speed, highly accurate. That can then be applied to systems for getting a robot to follow its operator, or accurate fast robot positioning systems. And then finally, in this category of application products, when COVID came along, actually around this time last year, we harnessed some of our technology from our sensor modules to create COVID mitigation solutions, including fever screening and a very sophisticated enterprise-grade social distancing tool that enables teams of people to work in close proximity but safely, and logging only potentially dangerous encounters with other people if they get too close for too long. And clearly, if somebody does fall ill, you have an ability to trace back and enable the other people that were in close proximity to isolate. And then finally, our people counting technology has enabled us to create a solution for density calculation so that you can ensure that you don't exceed the maximum capacity in your shop or building or office, and that social distancing can be maintained. Next slide. So actually that's it from me by way of sales pitch. Today's session is intended to be informative and educational. I'm going to hand over to Jan. As I said, I'll keep an eye on the chat. If you have any questions, please drop them in there. I'll monitor it as Jan speaks, and we'll try to answer as many as we can at the end of the session. So Jan, take it away.
Thank you very much, Greg. So what I'm going to do today is I'm walk you through the basics of time-of-flight technology. And I will explain you a bit what is behind that technology, but also a bit of background which will help you to evaluate if this technology is actually suitable for your application and what you can expect from such type of technology. So what is time of flight? Time of flight, as the name says, it measures the time of flight of photons traveling at the speed of light from a point A to a point B. Okay, photons, speed of light, I'll give you some update. Photons are the constituent of light, radio waves, gamma rays, X-rays, and so on. So, of course, for all of us, we know the visible range, which is kind of here, you know, with green in the center. And our sensors happen to work in the near infrared. Okay, we have different wavelengths we can offer to our customers. We can even adapt in case people need different ones. We do that mainly because that light is invisible and doesn't harm or doesn't interfere with normal operations and cannot see by the human eye. So what do photons do? So they travel at the speed of light, which is roughly 300,000 kilometers per second in air. They carry some energy, and they are usually never alone. Always come as a lot of photons. Sometimes you have single ones, but that is rather rare. So I did a simple calculation to figure out how many photons are, for example, emitted by a TerraRanger Evo, was one of our single point distance ranges. And the answers, assuming a couple of values, is that it emits 2.4 10 to the 13 photons, which is a number with 12 zeros. So it's quite a lot of photons. But of course, we cannot only send them out. We also have to get them back, and I will come to that later. So to get an idea what is 300,000 kilometers per second, because it's something you cannot really imagine, I have some example here. So from sun to earth, it takes about 8 minutes for the light. Okay, from the earth to the moon, 1.3 seconds. From a geostationary satellite, it's 36,000 kilometers away, it's 0.24 seconds. And just for you, between two people, okay, that was before COVID, but now with COVID, it's 2 meters, so it's 6.6 nanoseconds, 6.6 billionths of a second. Okay, as a rule of thumb, you can say it's about 30 centimeters per nanosecond in travels. So back to time of flight. What do we want to know? We want to know the distance between a sensor and a target. Can you see my cursor, by the way? Perfect. Okay, thank you, Greg. So what we need to measure is the time the photons which we send out from our sensor, and then they go to a target, they're reflected from the target and they come back. So they travel at the speed of light, we measure the time, and at the end we divide everything by 2 because simply it goes back and forth. So it does a round trip and we only need half of the distance. So for time of flight, ranging, and all kinds of time of flight sensing applications, you have 3 main ingredients which you have to look at to evaluate if that system works well for you in your application. First of all, it's the sensor. That's what you choose at the end once your application is defined. Your target, which is usually in the application, which is usually defined, and the environment, which is also defined or can be changed within certain limits. So the target can be everything where you point your sensor to. And the target is something which reflects the light back to the sensor. Ideally, it should do that, because if it doesn't reflect it back to the sensor, you will never be able to measure. And that's the first case we see top left here. It's a so-called specular reflection, which you can see on a mirror. It's an ideal specular reflector. So if you point the sensor to a mirror and the mirror doesn't point to the sensor back, so it's not perpendicular to the incoming light, it will emit the light somewhere. It will never come back to the sensor, and you will have a hard time measuring towards that mirror. So you will have to make sure that your target is always perpendicular and bringing the light back to your sensor. On the other extreme is the diffuse remission, the diffuse reflection of light. That's what you know of, for example, a matte white paint background, or a single piece of white paper is also a good approximation. So what it does, an incoming light is reflected back into all directions. And this is a quasi-ideal case for time-of-flight sensor, because no matter how the shape of your target, or no matter what the angle of your target is, you always get some photons back to your sensor. And then you see all the other kind of superpositions of these two effects. So you can have a diffuse, specular, a mixture. And that's typically what you see in the real life application. Imagine you want to count cars. So some cars, they come right out of the from the factory. They're nice and clean. So you will see spectral reflection. Might be difficult sometimes to catch them. Some of them are dirty or have seen a lot of sun, so they get rather diffuse, and you will have a better, easier way of getting photons back from them. So when you consider time-of-flight application, always look at your target first. So 2 examples. You can have a specular reflection, as I said, a mirror, aluminum foil, or you can have the other extreme, which is a very low reflectance object, like this one is a car painted in a very black. And no matter what kind of surface characteristic it has, it will never send any photons back because it absorbs all of them. A little hint, be careful, do not assume that the reflectivity, so the ability of the surface to reflect light back and to absorb light, which is the opposite of it, is not always the same as you see it by eye in the visible and for the near infrared region in which the sensors work. We usually have an example. It's a company where I have 2 people with 2 black pullovers. If you look at that in the near infrared region, some of them look like very good reflectors, others are very bad ones. So in principle, it's not very easy to assume what kind of reflectivity an object has by looking at it in the visible range. Then, of course, you can have surfaces which are irregular, okay? So what you can see here is that the path which the light travels has different lengths, okay? Depending on the sensor you choose, you can have sensors which give you an average, like the TerraRanger Evo does. You can have sensors which shows you the shortest one, and there are some sensors which give you a kind of value in between, depending on a mixture of how good it reflects and how far it is away. And you can have other effects where the light which is coming back bounces off, or the light which is going out bounces off a surface, goes to your object and comes back, and it is even longer than the other ones, which we call multipath effects. And typically this is something which happens areas where you have a lot of very good reflective objects in a scene in which you want to operate your time-of-flight sensor. Also, something interesting to know is how does light propagate? So you can have laser-based systems where the light is emitted quasi without divergence, so the light is not growing in terms of diameter of the beam, or you can have an emitter like an LED, for example, which works in the inverse square law. That means that the light the surface which is illuminated by the sensor grows with 1 over the radius. Okay, so This is important to know. For example, if you have a laser-based time of flight sensor, you will only measure one point, while with a system which has a divergent and therefore a non-zero field of view, you will get the average of a surface. For example, if you want to have a collision avoidance with vegetation, where you have little leaves and branches, etc., you might want to go for this version, because with a laser you have a chance that you go right through a tree or a bush. Okay, while this one covers a bigger surface and you have a bigger chance of getting the object. It depends on your application. So the light which comes back, I made a couple of examples here. Let's say we have an EVO 60 sensor, a target at 10 meters, and it's a 100% reflectivity mirror, okay, specular reflection. So even in that quasi-ideal setup, you only get 0.016% of the light back to the sensor. Then a bit more realistic, still a target at 10 meter, but 88% Lambertian surface. So this is a standard piece of paper, okay? You get 0.0014% of photons back, okay? And at 60 meters, it's even less. So you see that time of flight sensors have to be very sensitive to the photons which are coming back and measure the time which it actually takes to be reflected back and coming back to the sensor. Another ingredient for your time of flight sensing application is the environment. So what you can see here is a spectrum of the sun as it is measured in red here on the surface of Earth. This changes a little bit depending on the angle, because, for example, at noon, the sunlight will travel less distance through the atmosphere, while in the evening it will travel more. So you get different absorptions, for example, by the water, which is in the water vapor inside the atmosphere. So what you can see here, that in this spectrum, you see a couple of dips, and those dips mean that the amount of light at this wavelength is less at Earth's surface due to these kind of absorptions. And that's why we choose to operate our sensors at 940 nanometers, because we have this dip here and we have less light, which can change the performance of the sensor. So what is actually happening is that if you have too much light, the sensor will at some point saturate and will not be able to distinguish between the light which is coming back from your target and the light which is coming from the sun. It's a bit like a standard photo camera. If you overexpose and have too much light, it will not be able to make a nice picture, as it is with the time of flight sensors. The environment can also be less sunny. So, for example, fog and rain. What happens there is that you have situations in which the light is actually scattered back from particles which are inside the air. So that could be snowflakes, it could be fog, raindrops, dust, any kind of pollution. So you will have parts of the light coming back and parts of the light being scattered from the particles in the air. So depending on your application, you need to take into account how much light comes back and what is the ratio of the light which is coming back from your target and the ratio of light which can be scattered by the fog and rain in between, and you will get an idea how well your sensor works in the different conditions. Of course, we can help you with these things. If you contact us, we can get your estimates on those. So that's my short introduction to time of flight. I hope this helped you a bit better to understand the advantages, disadvantages, limitations, and design parameters for the application using time of flight sensors. I think we have a couple of minutes for questions, Greg.
Yeah, we do. Actually, Emmanuel popped a question in almost immediately that you started, so very keen there. Nice to see that. And the question is, actually, I think you've just really been speaking about it, but it's about sunlight and outdoor conditions. And the question is really specifically about EVO 3M and whether that's any more resistant to high illumination than other sensors in the EVO range.
This I would need to check in detail, but it depends a bit on the optics, and it depends a bit on the kind of target you use. So the EVO will probably work quite well on a target which is not too reflective in direct sunlight, so something grayish. It will not operate necessarily better than the Evo 60M under the same conditions. But as I said, it's usually very difficult to generalize this, because we have rarely seen targets which are the same in the applications we are doing in the company. So everything is a little bit different, and usually we propose to do a test first. But the general idea behind the sunlight resilience is actually that you make a sensor in such way that it does not saturate. So that means the light which is coming in is shielded from stray light, is filtered out with an internal filter which only lets pass the light at the wavelengths we operate at. But still, there's quite a lot of light at this wavelength still coming from the sun. So this has to be reduced as much as possible. And this is a tricky task and an optimization task between the cost of the sensor and the performance of the sensor. So you can still make it better, but at some point the cost will explode in building such a sensor.
Okay, thanks, Jan. I think that hopefully answers the question. Obviously, Emmanuel, if you want to have a deeper discussion with us afterwards, please feel free to contact us, and we'll be very happy to talk to you about your application and what the most appropriate sensor might be. One other question, actually, and I guess it's actually quite a common one, is about ultrasound sensors, and which are obviously very commonly used for distance sensing, and what the relative advantages are compared to an ultrasound sensor. And I guess by definition, what are the relative disadvantages of an ultrasound sensor?
Okay, so first thing I can say is a big advantage of ultrasound sensors is they can work underwater, which is something with the time of flight we are still working on. But okay, no, but without joking, is generally I would say the time of flight technology has a lot of advantages over the ultrasound. So it is very difficult to focus ultrasound in a reasonable way to a beam which is as small as it can be with the time of flight sensor. So actually what you see in terms of sensors with ultrasound, they have opening angles of several tenths of degrees, while time of flight sensors can go basically to divergence down to quasi zero or only a few degrees. That means in environments where you need to actually detect small objects, or where you have multiple sensors, like in where you need multiple sensors in confined spaces where you cannot allow for reflections, because the ultrasound will also bounce around. The time of flight is definitely an advantage.
All right, thank you, Jan.
I think nowadays, in terms of, I'm actually pretty sure, in terms of weight, say weight and build size, the time of flight sensors are equal or partially even smaller.
Okay, good. Thank you. I hope that answers that question. There are no other questions at this point in time. I'll just give it a minute for anybody to raise a final question. Can you just flick onto the next slide for me, Jan?
Yes.
So I just wanted to say that this is the first in a short series of these kind of technical exposés. So hopefully you'll be interested in joining us for the future webinars. May the 5th, we'll be looking at the people counting solutions using 3D time of flight, and why that technology is so exciting for that application. On the 10th of June, we're looking at the time of flight sensing for fill level measurement in silos, vats and tanks, and the advantages that brings. And then on July the 8th, we finish this little series ahead of the summer recess with an introduction to the thermal image sensing. We'll send out after the webinar a link so that you can register for any of these webinars. So I think at that point we'll draw it to a close. Thanks everybody for attending. We hope you enjoyed it. we'll seek to issue a recording of today's session. And as I say, please do join us for future webinars. Thank you very much.
Thank you very much for listening. Have a great afternoon.